Well, I guess you rolling. Like a big fat man, I've been sitting in the sand trying to figure out a way to make you understand. Well, I've been traveling over mountains in the valley too, trying to find me someone that looks like you. Well, I don't know why you had to flirt. Maybe you like to see me hurt. No more blowing the moon above. Shine down on the man's love. Well, if someday, baby, you get blue, just call me up and I'll come to you. Well, I won't be walking, I'll be flying. I won't be laughing instead of crying. Well, I don't know why you had to flirt. Maybe you like to see me hurt. No more glowing moon above. Shine down on the man in love. Work, y'all. Well, I travel over mountains and the valleys too, trying to find someone who looks like you. Well, I don't know why you had to flirt. Maybe you like to see me hurt. No more glow in the moon above. Shine down on the man in love. Oh, let me hear you one time. I see it now, listen now. I'm like a big fat man, I've been sitting in the sand trying to figure out a way to make you understand. Well, I travel over mountains and the valleys too, trying to find someone that look like you. Lord, I don't know why you had to flirt. Maybe you like to see me hurt. No more glowing moon above. Shine down on the man in love. I said shine down on the man in love. Shine down on the man in love.
All right, welcome back. It is Tuesday. We're going to continue on where we left off yesterday. Again, this is Computer Science 3, CSCE 310. And as always, I will be monitoring Piazza. We have a live QA over here. So if you've got questions, go ahead and post them. If you see technical issues, please go ahead and post there as well. Okay? So I did want to take a step back, though, and go back to something that we did yesterday, because I promised you maybe today we would actually program the repeated squaring kind of algorithm. And so we are going to do that now, and I'm going to show you two ways of doing it in Java, because this is something that you'll have to do in your second assignment. I've got it set up here for a small version where we'll do it on regular old integers, a, n, and m, 3 to the 77th. We're only taking the last two digits here, so we're going to compute the mod pow of that. I'm going to go over here to Wolfram Alpha to see what that value should be, so that we have a nice test case here that tells us whether or not our code is correct, or gives us good indication that whether or not our code is correct. I'm going to do this. Generally, when I've assigned this before, people try to convert it to binary. I've got the pseudocode that we put together over here on the right. People tend to change everything into binary strings. And this first version I want to show you, you don't need to do that if you know basic bit twiddling. So I'm going to show you a few things here. where you can shift the binary representation of an integer, say, left, you can shift it right. You can take a bitwise AND of stuff in order to isolate one or more of those bits. And so what we're going to do is we're going to transcribe the pseudocode on the right, and we're going to actually transcribe that into Java code over here. Okay, so I'm going to have a term, and that term is going to start out at A, right? And then I'm going to have a product, right? And I'll initialize that to 0, and that's the else statement down here. We need to check to see if that lowest order bit in n, which is B0 up here, is that 1, okay? So the way that you can do that is you can make an if statement. If n and 1, if that's equal to 1, then I'll go ahead and set this up so that product is actually equal to A instead, okay? Now let me walk you through this. Here's n, it's an integer, it's a regular old integer. There's a single and sign here. And, this won't even work in Java, it'll work in C or C++, but and is going to be a syntax error in Java because the thing on the left-hand side here, that's an integer, that's an integer. You can't take the logical conjunction, the logical and of two integers. In Java, you have to use Booleans. And so this is not, 2 ampersands here is not even going to work. But 1 ampersand, that's a little bit different. That's not the logical AND operator that you're used to. That's the logical AND operator that works bitwise. So if I had 4 bits here and 4 bits here of 2 numbers, say that it was 7, which would be 0, 1, 1, 1, and what we've got here 1, which is 0, 0, 0, 1. And if I AND those together, in fact, let me write this down. If I have 7, which in binary is 0, 1, 1, 1, and if I have 1, which in binary is 1, 0, 0, or 1, sorry, excuse me, there we go. And if I take the logical AND bitwise of these, then I look at the bits, and this is 1. 1 and 0 is 0. 1 and 0 is 0. 0 and 0 is 0. So it does not it does not produce what you normally think of as true and false. It produces another bit string basically, and that's what we're doing here. We're ANDing this with 1 so that we can isolate that last bit here. Whether or not these are zeros or ones, they all disappear because when I AND them with zeros, then I know that they're all going to turn out to be 0. That allows me to isolate the lowest order bit here. Okay. I'm also going to improve this a little bit more. Let me go ahead and pull up the pseudocode. I'm going to also improve this a little bit more. Instead of having this done in 4 lines, I'm going to have an initialization, and I'm going to use the ternary if-else operator that you may probably already be familiar with. But if you're not familiar with bit twiddling, then you may not be familiar with this ternary operator either. So what I'm going to do is I'm going to have a logical operation here. If that's equal to 1, then product will take on the value A. Otherwise, it'll take on the value 1. Oh, sorry. Question mark. There we go. Right. And I'll get rid of that. So let me walk you through this. This is a ternary operator. It's basically a shorthand for an if-else statement. So this is always going to be a logical statement that if the lowest order bit here is 1, then, that's the question mark, it's asking this question right here. And if that's true, then the value of this expression takes on the value of A right here. Else, and that's a colon there, it takes on the value of 1. Okay? So if it is indeed equal to 1, then just like in our pseudocode over here, it's going to take on the value A. Otherwise, it's going to take on the value 1. That's the product. And that allows me to do it all in one line. Okay? So now I'm going to go into a loop. But I'm not going to go into a for loop here. This for loop is operating on the second lowest order bit all the way up to the highest order bit. So I'm going to go into a regular while loop here. While n is greater than 0, then I'm going to continue working. Let's go ahead and take care of the pseudocode right here first. Term is going to be equal to term times term mod m. Right? That's pretty straightforward. Then we need to check the ith bit. So if, and I'm going to do the same thing that I did up here, but what I'm going to do is I'm going to say, is it the lowest order bit? I'm going to do that for the lowest order bit. Right. There we go. And right now that's not changing, so I'm always looking at B0, B0, B0. So we've got to make sure that we change this a little bit. But otherwise, product is equal to product times term mod m. Right, there we go. So far, I've not used any language-specific stuff. In fact, I could probably cut and paste this, and this would be perfectly valid C code. I'm not seeing anything here that is Java-specific. You could probably do this in most programming languages. Most programming languages do have bitwise operators, and this would work, right? I'm going to go ahead and return product at the end. Right? So now I am stuck right now in an infinite while loop here because n is never changing. I need to change it. I need to make progress towards the terminating condition of 0. So the idea here, let me go back over here, is that I've got, say, let's just take these 4 bits, B3, B2, B1, and B0. I've already looked at the lowest order bit, right? And I've determined that that gave me the initialization. I then need to look at the next order bit, next order bit, next order bit. So what I could do is I could dump that to a string like most students do, and then look at the is it the character 0 or is it the character 1? There's a much easier way of doing it though, using bit twiddling or bit manipulation. If I want to get access to this next bit, all I have to do is shift these bits over so that B1 becomes B0, B2 becomes B1, etc., etc. B0 will just fall off and go away. All right. Now there is a way. There's a cyclic shift, which you can do and make it go to the other side. That's not what I want to do because I don't care about it. In fact, I don't want to do that because then I'm just shifting the bits around, and I will never get to 0. Basically, shifting means that you are dividing by 2 because this is in binary, just like we talked about yesterday with large Karatsuba multiplication. Those shifts, multiplications by 10, they don't matter. Division by 10, multiplication by 10, that's just a shift, and this is a super efficient operation. So how do we do that in Java or most programming languages? Well, we use the less or the greater than. That shifts it left. If you want to, you can shift it. Or sorry, this shifts it left. Left and right are screwed up right now, and this shifts it right. That's what I want to do. I want to shift it to the right. Right? So I'll shift it right by 1. If you wanted to shift it right by 2, right, move all this stuff down so that B0 falls off, B1 falls off. You can do that. You can shift it by 2. You can shift it by 3, right? Each one of those is a division of a power by 2 then, right? This is a division by 8, which is 2 to the 3rd. I only want to divide it by 2, though, so that I can get that next lowest order bit. Now, Java is going to complain because this has no effect. This is an operation. What I need to do is n is equal to n shifted over 1. And I do believe you can go a shorthand here of, plus equals. You can do something like this as well, right? But I like to leave it like this because it makes it more explicit. How much are you're shifting n? You're shifting over 1. Some people would prefer, the the elided way of doing it like this. Okay. I'm going to go ahead and leave it like this, though. All right, let's see if this actually works. I've got it set up already with 377 and 100. Our answer again was 63. So let's see if we get the same value. There we go. It's the last one that's being printed. A bunch of other stuff is being printed up over here. So 63, and it's super efficient. You saw it executed almost immediately. We're not going into that exponential work of doing what is it, 77 or 76 operations, 76 multiplications. We're only doing a logarithmic amount of work down here. Okay. Now, what I wanted to do is to take this and how would you do this in big integer? Okay. So let's translate this. We've already translated the pseudocode over here into Java code that works on integers. Let's actually make it work on arbitrarily large numbers like big integer. Okay. So I'm going to have a big integer of a term, and I'll initialize that to a, just like above. I'll have a big integer of a product, and it's not going to. I guess I could do this, Let's go ahead and convert this big integer n here into binary immediately. So big, let's see, and here I am going to do a string because there is no built-in type that is going to allow me to store an arbitrarily large number of bits. I would have to manually create a byte array, and even then I'm storing bytes instead of individual bits. So in this instance, I will convert it to a string. I'll call it bin for binary, n.toString. And there's a nice little convenience function here that to convert it to a string, you provide a radix. A radix is the base counting system that you're in. Without this, it's base 10. You can go binary, which is what I want. You can go hexadecimal with base 16. I'm going to go with 2 here because I want the binary representation of it. So the product here, I just need to ask, is that lowest order bit 1 or not? So is bin dot char at, the character at, and then I need to get the last index, so that's going to be bin.length minus 1. If that is equal to 1, like I did up above, then I can use the ternary operator here. I'll go ahead and go with it. It should take on the value a. Otherwise, it should take on the value 1, but I can't do 1 because that is not a big integer. Instead, I have to use, say, big integer dot 1. There we go. And now the expression product takes on the value either a or 1, depending on whether or not that lowest order bit, which is being represented as a string, therefore the lowest order bit is being represented as a single character. If that's 1, then it takes on the value a, just like in our pseudocode over here. Otherwise, it takes on the value 1. Now here, I won't shift things down. You can kind of shift a string if you want. That's kind of weird. I'll just go into a for loop here. For int I, I'm using I in the pseudocode. So I'll start that at the lowest order bit here. I've numbered them 1, 2, 3, going right to left. That's not how string indexing works. So I need to start it at the end, at the second to last or lowest order bit. So that's going to be at bin.length minus 2. Right? And then while I is greater than or equal to 0, I'm going to work my way down. Right? I minus minus. I will put into the body the same as the while loop up here, but again, there's no shifting. So instead, term is going to be equal to term squared mod m, but I can't do that directly because I don't have operator overloading in Java. At least I don't have user-defined operator overloading. So you can't just a big integer times a big integer. You actually have to call the methods on it. Term dot multiply term dot, and then I'll mod out by, it was m. There we go. So I've squared the term, modded it out by m. Then I make that other check. That if the binary bit at index I, so if bin.char at I, if that's equal to 1, and by the way, I can use equal here just like most programming languages because characters are simple ASCII text characters. In Java, they happen to be full Unicode characters, but when you're working with the lower order ASCII text character set, there's no difference. So if you've got, if it's equal to I, then product is equal to product. And again, we can't just multiply. It's going to be times multiply term, and then we'll mod out by m. Remember, this is kind of similar to a fluent design pattern in that it returns. I mean, this is an object. It has this method, and it returns a new object. It's not exactly the fluent method, fluent pattern, because it is returning a different object, not the same object. But it's calling an object that we can chain all these calls together. Right? And then at the end, instead of returning null, just to get it to compile, I'm going to go ahead and return product. There we go. So I've got this set up here. Before it was returning null. I've just got this very large number. Of course, we can go ahead and keyboard mash all we want. We're raising 3 to this very large power modding out by 100 so that we only have to look at 2 of the values. And it's using the library up here to do the same computation. I'm just using that as a check, right? That ends up being my secondary, my test case, that there's something I know is correct. I'm going to compare it to something that I've developed, and I found, oh, 87, 87. That's another way of doing testing, software testing. You can build 2 independent solutions and then see if they agree all the time. If there are some things that they disagree on, then you have to go into an investigation of, is this one correct or is this one correct, right? When they disagree. So that's another way of doing testing. Over here, I did my testing with Wolfram Alpha. So that is how you can implement fast binary exponentiation in Java, and you'll be doing that in your programming assignment in the programming language of your choice. Again, some things to be aware of are: does your language support multi-precision values because it needs to, or do you need to bring in a library to do it? Can you do a simple bit twiddling, or do you have to treat it like a string, right? Okay. So let's go ahead and continue off where we left it yesterday with Strassen's matrix multiplication. And just to remind us of what it looks like, recall that the normal definition implementation of matrix multiplication of 2n by n matrices requires n to the n cubed, excuse me, multiplications and n squared times n minus 1, right? Additions, right? Right, n squared, and yeah, because there are n squared entries, and each to compute each entry, we only needed n minus 1 additions, but we did need n multiplications. So because each component was multiplied together, so both of those are going to be cubic, right? Both are cubic. So again, what Strassen did was he took a look. He just wrote out what the definitions were, and he started manipulating things around. And he came up, well, wait. There's a way to do this. Here's our regular matrix multiplication of 2 by 2 matrices. And he came up with an idea that, well, I can get away with fewer multiplications if I blow up the number of additions, and if I reuse some of the computed intermediate matrices. So M1 over here, for example, is that top left entry of the first one and that bottom right entry of the first one. We add those together, and then we multiply the top left and bottom right over here. And M2 is the top or bottom left entry of the first one, A over here, and the bottom right entry. And then once you add those together, you simply multiply it by the scalar value over here. This version here are all scalars. These are just numbers. These are not matrices, because this is the case of a 2 by 2 matrix. Okay? So instead of, normally if it's 2 by 2 matrix, as we said over here in the notes, that would lead to 8 multiplications. He was able to get away with only 7 multiplications, 1 multiplication for each one of these scalar values. There's, of course, a blow up in the number of additions. We've got 1, 2, 3, 4, 5, 6, 7, 8 up here for the actual matrix computation. And then 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 additions down here for the for each one of those the M computations. So Strassen's identities led to 1 fewer multiplication for 2 times or 2 by 2 matrices, but 18 additions, right? Now, of course, that is going to be worse, because if we compute over here that this would be, there would only have been 4 additions. 1 for each entry, and we're blowing that up to 14 more additions. So you might think at first, well, wait, that you're only saving 1 multiplication, and you're doing now 14 more additional additional additions. But on a computer, a multiplication is vastly more expensive than an addition. And this is true in most cases. There can be specialized hardware that tries to get a multiplication just as fast as an addition, and there are some architectures that may be able to do it. But in general, what we're doing is we're talking about in general. If I've got very large matrices, 1,000 by 1,000 matrix, where there's 1 million entries, 1 million entries, 1 million entries, leading to a 1 million entry matrix, right? Then that means that we're doing 1 million cubed operations. Let's ask Wolfram Alpha what that is. 1 million cubed. They're obviously going to be 6 times 3, 18 zeros after that. There, quintillion. We'd end up doing 1 billion billions, right? And the name for that is quintillion. It's exa for a standard unit prefix, etc. Right? So you might eventually, within your lifetime, you're going to have hard drives with exabyte capacity, I'm sure. So whether or not you need it, that's another question. But we've got a huge number of multiplications, a huge number of additions. If we can, moderately blow up the additions at the expense, that's an expense that we might be willing to incur if we can get the number of multiplications down. Okay. So I'm not going to go into like a huge example or anything like that, but you can see that this can be generalized. Right? So here's the generalization. If you're given an n by n matrix, say 16 by 16 matrix, what you can do is you can divide that into 4 quadrants. The 16 by 16 becomes 4 8 by 8s, 8 by 8, 8 by 8, 8 by 8, and 8 by 8. And then you have the exact same identities that worked before. But instead of these being scalars, being single numbers, these are now 4 by 4 matrices. And I'm adding this to a 4 by 4 matrix. I'm subtracting this 4 by 4 matrix, component-wise, of course. And then I'm adding this matrix over here. If you had the 32 by 32 matrix, then you could first split it up into 16 by 16. And nothing's stopping you from recursing even more. Then you would split it up into an 8 by 8, 8 and 8, then 4 and 4, 2 and 2, 1 and 1, and that's where the base condition of Strassen's takes over. All right, and we have the exact same values for each one of these m's. M1 is simply going to be the matrix ace of 0, 0, this matrix right here, the top left quadrant basically, added to the bottom right quadrant over here, top left quadrant over here, bottom left quadrant over here, etc. So the exact same formulas over here work on any sized matrix. Now there are some considerations here, right? Strassen's identities generalize to any n by n matrix. But the problem is to divide evenly each time all the way through the recursion requires matrices that are of size some power by 2, power of 2, right? So for example, in other words, n is going to be some power of 2 to the k for some k, okay? No problem. That's actually not a problem. We can use the same trick that we use with Karatsuba multiplication, where if you don't have a number that can be evenly divided, well, first of all, you can put 5 over here and 4 over here if you really want to. But you can force them to become 2 5-bit numbers by adding a 0 in the front. And now they're exactly the size that you need. You can do the same trick here. You can always pad out a matrix with zeros, left, right, bottom, top, it doesn't matter, without changing its structure, its values. All right. When you are done, you can trim. Right? Whatever the antonym is pad is, you're going to be left with a bunch of zeros. So if I've got a small matrix here and I need to pad zeros here, pad zeros here, pad zeros here, and then I go through Strassen's matrix multiplication, all those zeros, guess what? 0 times 0, 0 plus 0, they're all going to stay 0. And if I only had a 5 by 5 matrix over here that I expanded out into an 8 by 8 matrix with a bunch of zeros everywhere, then I'm going to end up with some 5 by 5 area over here in the matrix that has a bunch of numbers. Everything else will be 0. All I need to do is trim out all those zeros, and now I'm left with that 5 by 5 matrix. So it's just a technical issue that if you were actually program this, you would have to come up with. And in the past, I have assigned this as a programming assignment. And the first step that I encourage people to do is write a function that will pad out, create a new, given a matrix, it'll pad it out to a matrix that is of some power of 2 so that you don't have to worry about the small little details of how do I split this up exactly, right? If it's a power of 2, it's always going to work. 32 by 32, down to 16 by 16, down to 8 by 8, down to 4 by 4, down to 2 by 2, at which point you can then apply the base case conditions over here. Okay. So that sounds like a really cool algorithm. Does it actually, well, first of all, yes, it actually works. But is it an improvement? How much better is this? So for that, I'm going to go again back over to my overhead here, just a second. There we go. And here's my overhead. So let's let m sub n be the number of multiplications by Strassen on n by n on 2 n by n matrices. Right. Another issue here is, can you use this for non-square matrices? And absolutely, yes, you can. Guess what happens? You just need to pad it out so that it is square, and then you're left with whatever answer is left. So if you've got a 2 by 3 multiplied by a 3 by 2, 20 by 30 multiplied by a 30 by 20, you should end up with a 20 by 20. And you will if you pad it all out so that they're square and they're a power of 2. And then once it's all done, you're going to be left with a 20 by 20 submatrix in there somewhere, depending on how you pad it out, with the actual answer. So you trim it out, whatever that's a good question. Let me know that somebody's alive out there. Come up with an acceptable antonym to pad, right? Remember, again, there are two hard things in computer science: cache invalidation and naming things. So come up with a name for the opposite operation of pad for me. Thanks. So anyway, let m sub n be the number of multiplications by Strassen on on two n by n matrices. All right. So remember that we have 7 submatrices that we need to multiply together. We split them in half. So we've got n divided by 2. Right? Now, here at this point, I will, over here as an aside, well, wait, what's the actual input size here? I'm using the input size n. You can go, like we talked about yesterday, you can say that the actual input size here is n squared. So you're not actually taking it in half, you're actually taking it into 1/4 what it originally was, because you split it into 4 quadrants and you only give one of those 4 matrices to the subrecursive call. Right? Well, guess what? That's equal to n squared over 4 by this definition over here, which is equal to n divided by 2 squared. So we're talking about the same thing. Whether or not you want to consider n squared as your input, or whether or not you want to consider n as your input like I'm doing here, it's not going to matter, because you indeed are having it each time, having the input size. You're just, if you wanted to do this over here, you're just considering a larger input size, and therefore divided by 4 is still having it. It's just a different perspective. Right? So there are 7 recursive calls to matrices half the size. Right? How much non-recursive work are we doing? Well, we're doing a lot of non-recursive work. We're padding things out. We're splitting them initially. Then we're splitting them up and we're creating other matrices, or we're figuring out indices. We're adding a bunch of stuff. Remember, we're doing 18 additions non-recursively, right? But ultimately, for multiplications, that's what we're capturing here. So we're not doing any multiplications non-recursively. All the multiplications are done in the recursion or in the base case. And the base case here is going to be when you get down to a 2 by 2 matrix, m sub 2, you end up doing, we already counted them, 7 multiplications. So that is the base case there, but the base case is irrelevant when you apply the master theorem. The master theorem here, the coefficient here is 7. The coefficient here, or we have it each time, so b is 2. And just like with Karatsuba multiplication, we get away with an exponent here of 0, because this is going to be theta of 1. Right? It's constant. Well, 0 can't get more constant than that. So what is the relationship between a versus b to the d? Well, that's going to be 7 versus 2 to the 0. This is greater than. Right? Now, by the master theorem, I just want to make sure that I've got the exact number. It's going to be, so by case 3 of the master theorem, we get that m sub n is going to be theta n to the log base b of a, some polynomial. All we need to do is plug and chug, and this is going to be equal to theta of n to the log base 2 of 7. Right? Now, I would leave it in that form there because it's going to be theta. That's an exact expression. This is going to be an irrational number that goes on forever. But we can go ahead and put this into Wolfram Alpha to see what it looks like. Is it actually an improvement? Remember, the naive way of doing this was n cubed, so the exponent was going to be 3. This is, I could say that this is big O. I can't say that it's theta and terminate it, but I can say that it's big O of 2.8 something. Yeah, there we go. 2.807. And I'll just make it larger here, round up on that digit right there. Okay? So, yeah, it's an improvement. It's a slight improvement in the exponent. So you might ask yourself, well, can we go any further there? First of all, ask yourself, is that at all practical? Generally, no, unless you're talking about huge matrices. Like a million, 10 million, you'd have to find the crossover point for where it starts paying off is entirely dependent on your system hardware and the programming language, et cetera, et cetera. That's an engineering question. But generally for small matrices, no, it does not pay off at all. In fact, for small matrices, like if you're doing game programming and you need to do a linear transform and do matrix multiply two things together, generally you're talking about 3D graphics. And in 3D, everything is going to be 3 by 3. And so you use formulas. You expand out all the formulas and you just use the formulas which are going to be super fast. No loops, nothing like that. And you can even use lookup tables and stuff like that. So Strassens, in fact, let me go back to the notes so that I can just write this down. Here we go. So how much better is this? M sub n, the number of multiplications made by Strassen is order n to the 2.8. I forget where did we terminate it? 0.4, right? Approximately 280. Sorry, 7. There's a 7 in there. Yep, that didn't sound right. Likewise, the same analysis can show you that. There we go. That the number of additions is also order n to the 2.8074. It's going to end up being the same recurrence. You have 7 calls, but instead of plus 0 in the non-recursive cost, there's going to be a plus 18. Guess what? That's still a constant. So you will have the same A, same B, and same D in your master theorem, and so you'll have the same analysis. So it looks like we actually even cut down the number of additions asymptotically. We did not cut out the number. We blew up the number of additions by some fact. We went from 4 to 18 in the base case, right? But we only blew it up by a constant factor, and the actual recursion is actually cutting them down in total. So there is actually a huge constant sitting out front here that makes it kind of impractical unless you got extremely large matrices. But asymptotically, and if that's all we care about theoretically, then yeah, it's a big improvement for both multiplications and additions. But if you ever were to program this, you'll find that in fact, for the vast majority of applications, it's going to be much, much slower. Right? But there have been other improvements. Right? Just like there have been improvements with multiplication of integers, right? You had Karatsuba multiplication. You had then eventually the fast Fourier transform, a refinement by Führer just about 15 years ago. The paper that I was thinking about the other day, I actually pulled it out, and they achieved the n log n conjectured lower bound. So there is, and that was, I think that was published maybe 5 years ago, where they claim to have reached, through analysis, through some multivariate, basically a fast Fourier transform, they've been able to cut that down to just n log n. But here, there haven't been the same amount of huge improvements. Immediately after that, there's the Winogard, probably Vinogard, method that brought it down to order n, to the, it was, what was it, 2.375. So that was even bigger improvement, right? ... And that's why I'm putting order there. It's not exact. 3, 7, 5, 6. That'll make it a big O. Which just comes up with different identities. So instead, again, you sit there and stare at it long enough, and you start manipulating stuff, moving stuff around, and oh, hey, great, I was able to get away with only 5 multiplications instead. And so I can cut that down even further. The same algorithm was reanalyzed by another person in 2012, Williams, and she came up with an improvement. It was the same exact algorithm, but it was a better analysis, and she ended up reducing it just a sliver down to, what was it, 3727. There we go, 3727. So you see that she cut it down another couple hundredths. And as far as I know, that's the best at this recording time, or at this broadcast time. That's the best one that I'm aware of, and that was in 2012, so about 8 years ago. Now, again, whether or not these algorithms are practical, you probably want to look for heuristics. You probably want to find more structure in the actual problem that you're trying to solve in order to exploit that structure. Sparse matrices, for example. If there are lots of zeros, there are lots of tricks that you can do to do fast multiplication. Right? All right. So the overhead makes them impractical, but they are of theoretical interest because they're very good examples of divide and conquer kind of strategies. Here, we've got some suggestions for padding antonyms: trim, strip, D-pad. Okay, D-pad. Except for that's video gaming already. Right? You don't want that because the D-pad is the pad that you use to move, right? Move, remove, scrape. Good ones. DAP. I like that because it's pad backwards, right? Actually, that's my favorite right there. So I'll go ahead and upvote that one. Okay, great. Thank you for the antonyms. So at this point, it's kind of a segue into our next topic, but I still want to take a little bit of... so the next thing I'm going to cover here are solving linear systems and Gaussian elimination. And it's kind of related to divide and conquer. I cover this right after because we're still in the matrix kind of mode. We're thinking about matrix multiplication. It's a little bit different of what I want to do though. We're not talking about matrix multiplication anymore. Instead, we're talking about linear systems. But my segue for doing that is more matrices, right? Algorithms on matrices, Gaussian elimination, right? So again, it's not directly related to divide and conquer because it's not really a divide and conquer algorithm, but it involves matrices. So we're going to cover it here, but it is indirectly related to divide and conquer with respect to the determinant of a matrix, right? Related. So officially, linear algebra is not a prerequisite for this course, but the vast majority of students taking this course generally have taken at UNL that's Math 314. That's linear algebra. It's required for a couple of our majors, but may or may not be required for another. Certainly, you don't need what I'm going to cover and what you're going to actually program are not going to require an intimate familiarization with linear algebra. You know, bases, dimensions, and eigenvalues, and all that kind of stuff. We're going to keep it very, very simple. But I did want to talk about the determinant of a matrix. You might remember, especially if you've done very simple matrices, you might remember what a determinant is. If I've got like a 2x2 matrix, A, B, C, D. In linear algebra, they teach you all the time, here's the simple way of doing a determinant. It's just this cross thing right here. The determinant, if I call this A, the determinant of A is simply equal to A times D, top left to bottom right, and then you swing up to the top right and go down to the bottom left, minus BC, right? That's so if you've ever got a 2x2 matrix here, you can just go ahead and pull out that formula. That trick visually is what they usually show in linear algebra to determine the determinant. What if we had a 3x3? They also show you a visualization trick for this. A, B, C, D, E, F, G, H, I. Right? The determinant of this is you cover up the first row and the first column, right? And so the determinant is going to be equal to, I believe that it's A times, and then you take the determinant of this submatrix right here of E, I minus F, H, right? Correct me if I'm wrong there on Piazza. I think that you do take A as a coefficient over here, but I don't remember exactly. And then you've got another term over here, or then you subtract it, right? I'm doing all this off the top of my head from linear algebra a long time ago. You still cover the first row, but now you cover the second column. And you treat those four elements as a 2x2 matrix, so that you've got D, I minus F, G. And I believe B is your coefficient there. And then you add, and if you were to do this multiple with a generic n by n, you'd add, subtract, add, subtract, add, subtract. It's not telescope. It's telescoping. It's alternating, right? The sign out front of each one of these is going to alternate in sign. But the last one, you cover the first row and the last column, and you're left with DH minus EG. Right? And at that point, they stop teaching you these visualization tricks because you start to lose the forest for the trees. I've never met a linear algebra professor that was so. Maybe you can tell me if you have. I've never met a linear algebra professor that was so sadistic as to assign busy work of doing the determinant of a 4x4 matrix by hand. And that's simply because it is a terrible way of doing it. Right? So now that we remember this way of doing it, let's look at the actual mathematics here. Right? Get rid of this stuff. The actual mathematics of a determinant. First of all, what is a determinant? The determinant of an n by n matrix. And you have to realize that it is going to be a square matrix because it corresponds to n-dimensional space. You can talk about the determinant of a smaller, like a non-square matrix, but it doesn't make much sense because of what it captures. The determinant of a matrix captures, or basically models, the volume, is volume, right? Yeah, the signed volume of a linear transformation or a parallelogram in n-dimensional space. So if you were to, now we as humans can't really visualize four dimensions and beyond, so let's keep it with 3 dimensions here. If I had a 3 by 3 matrix, the determinant of that defines a parallelogram in 3 space. In fact, if you want to keep it even more simple, think about it as a 2 by 2 matrix so that you can write it down on a piece of paper. A 2 by 2 matrix can correspond to just a parallelogram. Here's one vector, one row, another row, and then the mirroring of those rows will form a parallelogram. The determinant gives you the volume, or in this case, the area of that parallelogram. So in 3 space, you're talking about a 3-dimensional parallelogram, right? Not necessarily a cube, although it could be, but a cube that's shifted some way off of its axis that's represented by a linear transformation. The volume of that parallelogram will end up being the determinant of the matrix used to describe it. That's why if you have a unit cube, that corresponds, I believe, to the identity matrix, and the identity, the volume of, or the determinant of an identity matrix is always 1, giving you the unit volume of a cube, right? But I'd have to really think about that. I think so. Go ahead and confirm or deny on Piazza. Thanks. So the official definition of the determinant is this math that I am going to simply cut and paste. It is in the book, or the lecture notes, I should say. There we go. So what does that mean? So the determinant of a matrix, an n by n matrix, is the summation of all these things of the sign of this sigma here, of the product of all the elements in that row or whatever. It's basically what we did visualizing down here. What is this thing? S of n is the symmetric group on n elements. In other words, it's the set of all permutations. So if I take the approach that the sadistic linear algebra professor tries to give as busy work, then I'm going to be doing n factorial work, right, to be doing this, because this is going to be summing over all elements in this symmetric group. The symmetric group is simply just take, if you've got n elements, take all permutation of those n elements, of which there are n factorial of them, and you have to do this computation for each one of those things. Basically, it's the permutation of a particular column or row, or I guess it would be column right here. It's basically what we were doing on a piece of paper, but in higher dimensions, right? That's not going to cut it. So there is a divide and conquer approach, and this is how it's related to the divide and conquer topic that we've been looking at. So here's more complicated math, right? So the divide and conquer approach is simply to just take, again, this is basically what we were doing on the piece of paper. We took this S here, which is the plus or the minus, depending on whether or not J is even or odd. Up here, that corresponds to the sign over here. The sign of a permutation, you can define that, I believe, even or odd, depending on the number of transpositions there are. Don't worry about it, right? That's linear algebra. That's kind of not relevant here at all. But this is basically what we were doing on the piece of paper. We were taking the first row, the jth column, after we permuted it, right? And then what we did, this summation right here, that's pretty straightforward. Can I highlight it? No, I can't. That's pretty straightforward. But then what do we have over here? We have the determinant of J, where J is the n-1 by n-1 matrix obtained by deleting row 1 and column J from A. Right? So this is the official definition. If you transform that into a definition that has a divide and conquer kind of approach, a recursive approach because of this determinant right here, then you can see immediately that, yeah, it's a divide and conquer approach, but it's the same thing as up here. It's going to end up being n factorial. I don't remember if I assigned it this year, but in years past, I've had students actually do the analysis here. All it is, it's pretty straightforward. All you need to do is come up with a recursion that the number of multiplications or whatever you're trying to do is going to end up being, you do n recursive calls, because that summation there there are n of them, and then you have a recurrence that does not decrease by half each time. It only decreases by 1. So if you go back to the very beginning of divide and conquer, where we covered you can decrease by a constant or you can decrease by a constant factor, we're only decreasing by a constant here because this is going to end up being an n minus 1 by an n minus 1 matrix, and then we end up doing a linear amount of work over here. If you expand this out, solve it. Master theorem is no help here because it's not in the proper format. If you expand this out, you'll find that this is going to be order n factorial. Right? I think I just invented new. I was about to write a question mark here. So if you're still having fun with antonyms, go ahead and think of what should this mean, right? Instead of a exclamation point, what if we put a question mark there? What kind of math should that correspond to, right? All right. So bad. Even a divide and conquer approach here is not going to help us. Instead, what we need to do is we need to find structure and exploit that structure. So observation. Right? This is just a result from linear algebra. The determinant of an upper triangular matrix, or some upper diagonal matrix. Sometimes this is called a triangular matrix. In fact, I'm pretty sure that if you were to ask a linear algebra professor, what do you call that thing? They're probably going to say a triangular matrix. Is simply the product of its diagonal elements. Right. So what does that mean? That means if we can take a matrix, an n by n matrix, and transform it in such a way that we don't change the determinant, but we can make it appear like this. These are numbers up here, right? And these are numbers on the diagonal, but everything below the diagonal is 0. Right? This is why I call it upper diagonal, because it's only the upper diagonal potentially has actual non-zero numbers, right? May be non-zero. Of course, they could still be 0, but and you'll get other results. But what we want now, what's the determinant? The determinant of A, if you've got it in this form, is simply the sum of I running from 1 up to n of a sub I. In other words, take a sub 1, 1, a sub 1, 2, 2, 3, 3, 4, 4. Take everything on the diagonal and simply just take the sum of did I say sum or product? That's a good. It should be I believe that it should be the product, right? So, good question. I'm confusing myself and I don't remember now. But oh well. I'll see if I can look it up really quick. I think it's the product. I'm 90% sure that it's the product, but I'm not sure. Anybody tell me on Piazza? Help me out here. Okay, yeah, I was right. It's the product. Okay, there we go. So it's the product, not the sum. There should be a product right here. There we go. So just take A11 times A22, A33, etc., all the way down. So can we do that? Can we come up with an algorithm to take an arbitrary matrix and turn it into an upper diagonal triangular matrix, preserving the properties? And it turns out that you can, right? You can, you can apply various elementary operations to a matrix to make it into an upper triangular matrix, upper diagonal matrix, and preserve the value of the determinant. I'm going to show you those, but I'm going to show it to you in a different context. The context that I'm going to show it to you in is our linear systems. All right? Okay. I want my other pen. There we go. So, what is a linear system? Even in grade school, you did linear systems. You just didn't call them linear systems. I'm going to give you a linear system here, and now we're going to solve it. So 3x plus 2y is equal to 35. Right? Now, is that a linear system? Can you solve for x and y? No, because you only have one equation here. You can solve everything in terms of x if you want to by taking 35 minus 2y all over 3. I've just solved for x there. But without knowing y, I can't determine x. Without knowing x, I can't determine y. So I need a system of linear equations. I need another equation here, x plus, say, 3y is equal to 27. Those are the examples from my notes so that I think that it comes out nice and clean. But now that I've got this, what I can, now you can solve for x and y. All right, for this particular one. In general, you may not be able to solve for it because your system could be indeterminate or inconsistent, and we'll talk about that later, right? In a moment here, actually. So here, the way that you do this is by solving for one, and I did that already, and then you plug it into the other. If I plug this in, I get 35 minus 2y all over 3 plus 3y is equal to 27. And now look, I have an equation with one unknown because I solved the other unknown in terms of the second variable, and now I can go ahead and figure this out. This is going to be, let's multiply by 3 all the way through 60, 81, right? So I'm going to multiply both sides by 3, right? I can do that because that's valid math. As long as you're multiplying both sides by 3, so that I can get rid of this. 35 minus 2y, and this becomes 9y. Right? I can collapse these two, so 35 minus 7y is equal to 81. Right? I can subtract and take this onto the other side, and that's going to be 46. Right? Negative 7y. Right? And then finally, y will give me 46 divided by 7, and that's a negative. So I guess it didn't come out to be nice and pretty. But what I can do now is I can take that and I can plug it back into either one of these equations. You can plug it into this same equation that I did up here, or I can plug it in over here, or I could even plug it in over here, and I would get out x from that. I'll leave that as an exercise because, again, this is kind of middle school kind of math where you're given a system and two equations here. What if I gave you a system in 3 unknowns, x, y, and z? Right? What if I gave you, say, 3x plus 4y minus 7z is equal to 35? Right? What if I gave, and then how many equations would I have to give you now? If you've got 3 unknowns, you need 3 equations. So we need 2 more. Right? In order to specify, to determine the system. As it is right now, this is an indeterminate system. There are an infinite number of x and y and z values that will satisfy this equation over the reals, right? So, what about in general? What about n dimensional linear equations? How do we solve for those? Well, again, only a sadistic middle school teacher or a linear algebra professor would assign, say, any system more than 4 or 5 or 6 or 7, right? I had in my memory, I had such a sadistic linear algebra professor that gave us a system of 4. But of course, because I was also in computer science, I said, nuts to this, I'm not going to do this all by hand. And so I simply just programmed it because I knew about the algorithm that we're about to look at here in a second. Okay. Before we do that, though, I need to make sure that we understand two things here, some caveats, right? Not all systems are solvable. Not all systems have a solution, you should say. X plus 7y is equal to 8, right? And then 2x plus 14y is equal to 16, okay? Try as you might, you will not be able to solve this. Let's go ahead and try, though. Right? I can get x to be in terms of 8 minus 7y. When I plug that in down here, what do I get? Right? I get 2 times 8 minus 7y plus 14y is equal to 16. Okay? So 16, hey, great, that'll cancel out, and so I can take that out. So let me be explicit about it. 16 minus 14y plus 14y is equal to 16. Okay, 16s cancel, 14s cancel, and what am I left with? A big revelation that 0 is in fact equal to 0, right? It didn't end up solving the value of that variable there, right? This is an indeterminate system. Graph these out. Since this is a dimension 2 system, you have x and y. You can get this into a standard form, solving for y. Y is equal to, say, negative 1/7 x plus 8, and y is equal to, you can divide by 2 and get the exact same equation. In fact, that's the observation that you should be making here. The second equation here is simply twice the first. All I did to get this indeterminate system was take the first equation, multiply both sides by 2, which gave me double everything. Right? It's the same equation. Right? So really, I only have one equation, meaning that I cannot solve the system. But what does it look like visually? If you were to map this out, then it's going to be negative, what is it? Plus 16, negative 2 on the other side, well, 1/7. There we go. So, same slope, different y-intercept. What does that tell you about these two lines? They're parallel lines. They're actually parallel lines, not my drawn parallel lines here. They will never intersect. What were we doing before when we solved the systems? Right? We were finding where two-dimensional lines intersect. That's our solution right there. Right? That visually, that's what we were doing when we were solving a linear system. We're finding the intersection of these two equations. If there is no intersection, then it's an indeterminate system, and you cannot solve it. Right? Here's another example of where this will fail. All right? Let's see. Here we go. X plus 7y is equal to 18. Or sorry, 8. 2x plus 14y is equal to, doesn't matter, but 20. Okay? This is the same one as before. This is definitely not just the first one multiplied by 2. It's multiplied by 2 on the left-hand side, but on the right-hand side we get something else entirely. Let's try to solve it. X is equal to 8 minus 7y, just like before. Plugging that in over here, I've got 2 times 8 minus 7y plus 14y is equal to 20. This is 16 minus 14y plus 14y equals 20. Well, these two cancel out. I can take 16 onto the other side, and guess what I get now? 0 is equal to 4. Hopefully you don't treat that as a big revelation like we treated the 0 is equal to 0 revelation. This is inconsistent. Right? How do I want to interpret? I forget how. Oh, sorry. I think I screwed up. Yeah, that's why I'm confusing myself. This corresponds to the situation where you've got two parallel lines that never intersect. Right? The previous solution, which I've got down here, this is not corresponding to two parallel lines. This is corresponding to where the two lines are exactly the same. I think I screwed up my math over here, and that's why. This should because when I brought 2 onto the other side, I should have made this 8. They're the exact same equation. It's like writing one line and then writing the other line right on top of it. There are an infinite number of solutions here. There are no solutions here because these two lines will never intersect. They're parallel lines, and the solution corresponds to an intersection point. So it's an inconsistent system. The previous one was an indeterminate system. There are no solutions to this system. So you do have to be careful. When we ultimately look at the following algorithm that we're going to be looking at, then I'll tell you how that manifests itself with Gaussian elimination. Okay? But it's probably going to take us into tomorrow to do that. Sorry. What I wanted to do is I do want to show you the basics of Gaussian elimination. In case you've never taken a linear algebra course before, it's basically what we were doing with, solve for one variable and then plug it into another equation. Solve for another variable, plug it into another equation. We're going to do it for a system of dimension 3. So here's my system. 3x1 minus x2 plus 2x3 is equal to 1. 4x1, I've been meaning to change this system for quite a while here because it doesn't come out to nice whole integers, but so be it. I'll just Google and like a linear algebra primer and steal their examples, and then hide it by the fact that I'm going to multiply it by 2 or something like that. 3x plus 3x3. Note that I'm not using x, y, and z here anymore. I'm using x1, x2, x3. That's because once we get into 4 dimensions, 5 dimensions, we run out, well, we're at the end of the alphabet, we run out of letters. So I'm just going to keep it generic with subscripts instead. So here's our system. What we're going to do is we're going to create what's called an augmented matrix. What I'm going to do is I'm going to take the coefficients of all of these things and make an n by n plus 1 matrix. So it's not exactly a square matrix anymore. The system itself is square, but we also have this right-hand side full of scalars, just values, that we also need to take into account. Because what we can do is we can multiply an equation by a scalar of 5 on each side, as long as we do it to both sides. So that corresponds over here to doing an operation on a row. To do that, I need to create this augmented matrix. The coefficients here are 3, 4, 1, -1, 2, and 3, 2, -1, 3, and sometimes people like to draw an imaginary vertical line here to separate 1, 4, and 5. Right? This corresponds to the system on the left-hand side. This corresponds to the vector on the right-hand side. You are essentially trying to solve a matrix with a bunch of coefficients multiplied by an indeterminate vector where x naught is equal to x1 dot dot xn, right? A vector of variables that you need to solve for, and that's equal to a vector b on the other side, denoted as b1 dot bn. This is b1, b2, b3 all the way, right? So you're trying to solve for this vector right here, basically. If this is just one variable, it would look like this: ax is equal to b. You need to solve for x by taking a onto the other side. If there are 2 variables, then it looks like a 0, 0 x1 plus a 1, 0, 1 x2 is equal to b1. A 1, 0 x1 plus a 1, 1 x2 is equal to b2. Right? So all I'm doing is I'm taking these coefficient and scalar values out and putting them into this augmented matrix right here. Now we can do several things to this. We can do anything that we can do legally to this equation up here, multiply it by both sides, take one value onto the other side, subtract by a scalar value on both sides. Basically, or I didn't even have to write it like this. I could take this row, this equation, and make it the second equation. I could take this equation and move it up here. I could take a column and transpose it with another column, as long as I keep track of how I do that. Because if I take this column and swap it with this column over here, that means that the original variables are now swapped. We've got x2 and y3, or x3, right? Let's see. Okay, yeah, we're still good. And we're good on time, too. So I'm going to now apply a series of elementary row operations, right? What I want to do is I want to make this, to make this look like an upper triangular matrix with, of course, there's b values over here. I want to make these three numbers, this number, this number, and this number, I want to make all those 0, right? To do that, I can do a series of elementary row operations. We're going to focus first on these two right here. We want to make the first element in row 2 and the first element in row 3, we want to make those zeros. How do we do that? Well, in terms of row number 1, what I can do is I could subtract 4/3 row 1 from row 2. Right? Why will that work? Well, if I multiply this by 4/3, I get 4, and if I subtract it off of the second row, that makes this 0. In fact, the relationship between these two numbers has told me what I need to multiply by and subtract by in order to make this one 0. What about the second row, or the third row here? This should have been off of this one. There we go. I need to subtract 1/3 times row 1 from row 3. I won't beleaguer you with the algebra. What does that look like at the end? So the first row is the same. Oh, let's do one at least. So we know that this is 0 by our choice of 4/3. I need to subtract 4/3 from row 1 from row 2. So 4/3 of -1. So 4/3 times -1. And I subtract off from row 2. So 2 minus this. And that'll give me 10/3. Right? It's 2 minus 4/3 row 1. Yep, I don't need this. That's multiplication right there. So plus, that's why. I was confusing myself. So if I get this in same order terms, that's 6/3, and then that's where I got the 10/3. So what about this entry right here? 4/3 times row 1. Right? So row 1 is 2 times 4/3. And I subtract that off of row 2. Row 2 is -1. And so I end up getting -11/3, right? Last one here. From 4, I subtract 4/3 times 1. And that's going to be 8/3. Right? This is why I regret this example, because I wanted everything to turn out to be nice integers instead of a bunch of fractions. Right? We're going to make this 0. And again, I'm not going to beleaguer the algebra here. This is going to be 10/3, 7/3, and 14/3. Okay? Then what we need to do is we need to make this one 0. Right? So I need to subtract how many times row 2. By the way, we no longer do this in terms of row 1. Right? If we did this in terms of row 1, then that reintroduces this non-zero value over here, and the thing that we just made 0, we reset it to something that's not 0, which is not what we want to do. So we're going to always do it in terms of the row immediately above, because if we've set all of these up to 0 already, then that means that they won't affect anything over here. All right? So we subtract 1 times row 1, all right, excuse me, row 2 from row 3. And when we do that, we get, again, the top row, and in fact, the top 2 rows now are unchanged. 0, 10 thirds, negative 11 thirds, 8 thirds. This becomes 0 because I'm subtracting 10 thirds, 1 times 10 thirds from 10 thirds. I need to subtract 1 times 11 thirds from 7 thirds, but since this is negative, that ends up being plus, so that's 18 thirds, which ends up being 6, right? Yeah. So this last row will end up being full integers at least. And then I need to subtract 1 times 8 thirds from 14 thirds. That gives me 6 thirds, which is going to be 2. There. What does that correspond to with respect to our equations? What we've done with these simple matrix operations is we've made it so that we've got the following system. 3x1 minus 1x2 plus 2x3 is equal to 1. That's our first equation. But since we've got this as a 0, that first unknown in the second equation has dropped out. 10 thirds x2 minus 11 thirds x3 is equal to 8 thirds. And then finally at the very end here, we've got that 6x3 is equal to 2. How has that convenienced us? It's convenienced us because now the last one is an equation in one unknown. All we need to do is say x3 is equal to 1/3, taking 6 over to this side. Now let's go up one more equation. There's actually only one unknown here because we've already figured out what x3 is. Plug that in over here, right? Take that onto the other side, and then divide by 10 thirds, multiply by 3/10, and you get, spoiler alert, I'm not going to do all the math here, you get 7 thirds. So x2 ends up being 7 thirds. Right? Yeah, or 7/6, sorry. Now we've got both of those unknowns. All we have to do is plug that one over there, plug that one up there, and then take all those onto the other side, and divide by, take the 3 onto the other side, and we're left with x1 being 1/2. So we ended up solving this system of 3 values here by doing elementary row operations on a matrix rather than, on a piece of paper, a plug and chug kind of things. And okay, well that equation looks like it'll be easier because I can get it into a integer form or something like that. All right, this was much more systematic. The first part here was called Gaussian elimination, making it upper triangular. The second part here was called back solving, where we work from the bottom. So we've made all this 0, so that the last one is going to be one unknown, so we can solve for that. Once we've got that variable value, we can solve for the next variable value, then the next variable value, etc. When we come back next time, we will cover all of that in pseudocode, because of course you are going to be programming this for your next programming assignment. But I just wanted to really quickly talk about the two edge cases that we were looking at before. An inconsistent system, remember, is one with no solutions. It has parallel lines. That corresponds to parallel lines in n space. So for a system of 2 equations, 2 unknowns, then you're talking about two lines in 2 dimensions. What does it mean with Gaussian elimination? How do we detect that there are no solutions? Well, inconsistent means that we eventually got down to 0 is equal to 1 or something, or 0 is equal to 4, right? Which we know is not correct, right? So if the last row is all zeros except the last entry, right? It'll end up looking like this: 0, 0, 0, 0, and then we've got something else over here, say 4, just to be consistent, right? And then here's the rest of the matrix, here's the augmented matrix, and these are numbers, we don't care what they are. This means that with no variable values on the left-hand side, that's equal to 4. In other words, 0 is equal to 4. That's how we can detect an inconsistent system. Once we've done Gaussian elimination. 0 is along the diagonal, except for this last one over here is some non-zero value. Right? What about an indeterminate system, where there are an infinite number of solutions? In other words, the two lines completely intersect. They intersect at every single point. So what that would look like is an indeterminate system means that you have, say, two equations, or two unknowns, two equations, but one of those equations is simply just a scalar, a scaled value of the first one. So what will that look like after Gaussian elimination? It'll mean that you've eliminated entirely that equation. The left-hand side will all be zeros. The right-hand side will be 0. Because remember, we got 0 is equal to 0 when we tried to solve an indeterminate system. And you'll get the same thing when you apply Gaussian elimination. So Gaussian elimination not only solves a system, but it also, you can look, before you start back solving and dividing by 0 everywhere, because that's what will happen when you try to take this onto the other side, the coefficient onto the other side, or 0 divided by 0 in this case, you can check what does that last row look like. If that last row is all zeros, stop. There's no point in solving because it's indeterminate. If it's all zeros except for the last one, stop. There's no point in solving it because it's an inconsistent system. When we come back next time, I'll present the pseudocode, we'll analyze it, and then we might talk about your midterm that's coming up next week. All right. Have a good day.